Hi everyone, this will be my first video class. What I'll be doing is I'll be starting from unit 3, but unit 3 is comparatively easy when you compare to unit 1, unit 2 and unit 4. So I'll be not going in detail in every theorem, fine. Wherever I feel you might have get some doubt, those things only I'm going to clarify. So I'll start with Weierstrass theorem for sequences. So before going to Weierstrass theorem for sequences, we'll see what do you mean by pointwise convergent and uniformly convergent. You know what is pointwise convergent, right? So the definition says if you have a sequence of functions, say fn of z, all defined on some region omega, we say that these functions fn of z converge to another function f of z, which is also defined on omega uniformly, provided given epsilon greater than 0 and given a point z0 in your region or in your domain omega, there exists some natural number which I'll call it as nz. So why I'm telling nz means this nz0, because this natural number depends on the point which we have taken, that is z0. So given epsilon greater than 0, there exists, and given z0 belonging to omega, there exists a natural number n which depends on z0. So I'll call it as nz0, such that mod fn of z minus f of z will be less than epsilon whenever for all n greater than or equal to nz0. So this is what we mean by pointwise convergent. And next we have uniformly convergent. So uniformly convergent is more stronger than pointwise convergent. So the definition goes like this. So a sequence of functions fn of z defined on omega is said to converge to a function f of z which is also defined on omega uniformly if the following follows, that is, given epsilon greater than 0, there exists a natural number n such that mod fn of z minus f of z is less than epsilon for every n greater than or equal to n0 and for all z belonging to omega. So in this definition you can see that the natural number which we have chosen doesn't depend on any z. It is true for all z. So there is, for all z we have only one n0 such that mod fn of z minus f of z is less than epsilon. So here is the picture which I am telling about, fine. I suggest you to use earphones because the sound is not so clear as I feel. Okay, now we'll come to Weierstrass theorem for sequences. So basically what it says is if you have a sequence of functions fn of z where each fn of z are defined on region omega n and fn's are analytic there, fine, and these sequence fn of z converge uniformly to a function f of z on every compact subset of omega, not on omega, but we are telling that on every compact subset of omega, then we have to prove that f of z is also analytic in omega. That is the first task. And the second task says that if you take the sequence of their derivatives, say fn dash of z, we have to show that this sequence also converges uniformly, and we have to show that it converges uniformly to this function f dash of z, which we have already obtained it as f of z. Since fn of z and f of z are analytic, obviously their derivatives will also exist. And I am just talking about fn dash of z and f dash of z. Once if you prove that for f dash, fn dash and f dash, then you can prove for any higher derivatives. So this is the task, fine. What I will start doing is to read the proof which I given to you so that you can follow it from the book. The same book I am also using, fine. So we start with a point z0 in omega, and later in that theorem we are telling that there exists some r greater than 0 such that there is a neighborhood whose closure is contained in omega. So my question is, how is this possible? If you find some z0 belonging to omega, how can you find a neighborhood such that the closure of that neighborhood is contained in omega? So the basic fact, we know that omega is an open set. So whenever you we have an open set, then every point is an interior point. That means you can find a neighborhood which is contained in omega. That is what the first line says. But the next line says that then there exists some n naught belonging to n, such that n there is another neighborhood nr of z naught whose closure is contained in omega n for all n greater than or equal to n naught. So my question is, how is this possible? I can show that this neighborhood is contained in omega because omega is an open set, but how can I find a neighborhood which is contained in omega n specifically and for all n greater than or equal to n naught? So what we do is, we know that omega is nothing but union of omega n's, and omega n are also open sets. So if z belongs to omega, z has to belong to union of omega n. That means z has to belong to some omega n naught. So once if z belongs to some omega n naught, I know again omega n naught is an open set. So again we have a neighborhood which entirely lies in omega n. But I know omega n is contained in omega n plus 1, which is contained in omega n plus 2, and so on. So we are telling that there exists a neighborhood nr of z naught whose closure is contained in omega n for all n greater than or equal to n naught. Fine. Once that is true, now you can take inside that neighborhood, you can take any gamma to be a simple closed curve, and we know that all fn of z are analytic in this. Not all fn of z, but all those fn of z for n greater than or equal to n naught. We know that these functions are analytic. So by Cauchy theorem, it follows that integral over gamma fn of z dz is equal to 0 for all n greater than or equal to n naught. Fine. Later they used the fact of that fn converges to f of z uniformly, and they changed the integral and limit, and at last they got integral over gamma f of z dz is equal to 0. By this they have concluded that f of z is analytic in the compact set or the neighborhood nr of z naught. So again question is, if integral over gamma f of z dz is 0, how can we say f of z is analytic? We know that if f of z is analytic, then integral over gamma f of z dz is equal to 0. But here the task is the other way. The given integral over gamma f of z dz is 0, but how to claim that f of z is analytic? Fine. So here there is a partial converse theorem for Cauchy's theorem, which we call it as Weierstrass theorem. So Weierstrass theorem says that if f of z is continuous in your region and integral over gamma f of z dz equal to 0, then f of z has to be continuous. This has to be true for every gamma inside your disk. Fine. So we know that f of z has to be continuous. Why? Because I know fn of z are analytic, so they are continuous, and we are telling that these sequence of continuous functions are converging uniformly to f of z. Therefore f of z has to be a continuous function, which you have already learned in 10th semester. So we have proved that integral over gamma f of z dz is 0 and f of z is a continuous function inside your disk. Therefore f of z has to be analytic in that neighborhood. Since z0 was any arbitrary point, you can show that f of z is analytic at every z0. Therefore f of z will be analytic inside your omega. So I have sent the picture of this, which you can see. So we have completed the first part, that is showing that f of z is analytic. Now we are going to the second part. So we had to show that the sequence of functions fn dash of z converges uniformly to f dash of z on every compact subset of omega. So in the second page, after proving that f of z is analytic, we started with take r greater than 0 as earlier and consider C to be a positively oriented circle around z0 with radius r. You can start from the same thing. We are taking the same neighborhood which we had taken before also. Fine. But here we have to show that sequence fn of z converges uniformly to f dash of fn dash of z converges uniformly to f dash of z is my task. So first we have proved that fn dash of z converges to f of z, not uniformly but pointwise. But I think we need not write this part, because we have to just prove that fn converges to f dash of z uniformly, right? So why should I show that it converges pointwise first, and then why should I show it that it converges uniformly? Instead of that, we can directly show that it converges uniformly. Fine. So in the second page, you will start from, therefore fn dash of z equal to 1 by 2 pi I integral over c fn of zeta by zeta minus z squared d zeta, and you start proving that limit n tends to infinity fn dash of z is equal to f dash of z. This part you can skip, because in this part we are just trying to show that fn dash of z converges to f dash of z pointwise but not uniformly. Later we will show that it converges uniformly. If at all, if you want to write this step, there is some mistake in this part. So you don't start with fn dash of z, but you start with fn dash of z naught. Fine. So fn dash of z naught will be equal to 1 by 2 pi I integral over c fn of zeta by zeta minus z naught whole square. That means what I am trying to say is, already the point z naught has been given to you. So given z naught, there exists some n naught. Are you understanding? This n naught is dependent on z naught, and at last you are proving that limit n tends to infinity fn dash of z naught is equal to f dash of z naught. That means given epsilon greater than 0, there exists, and given z naught belong to you, there exists some n z naught, or which I am calling it as n naught, such that mod fn of z naught minus f dash of z naught is less than epsilon for every n greater than or equal to n naught. This means it is pointwise convergent, because if you, instead of taking z naught as in the question, if you take z and zeta, then while taking limit you have function of two variables zeta and z, which we don't know how to take limit. So instead of that, you take, instead of z, for any, they given any z such that mod z minus z naught is less than rho. You don't take any z, you particularly take z naught, then only this part works. Otherwise you can totally skip this part. Fine. And you can directly go to the next part. So in the next part we are trying to show that, I have written that to show that sequence fn dash of z converges to f dash of z uniformly on in mod z minus z naught less than or equal to rho. That means in some compact set. I think here there is no much thing to discuss. Of course the equation looks very complicated, but it is not actually complicated. What we are trying to do here is, you start with some epsilon greater than 0, which I am calling it as epsilon dash, which is epsilon dash equal to epsilon times r minus rho square by r. Fine. So here in this disk you take any z. Fine. But I know that fn of z converges to f of z uniformly on every compact set of omega. That means given epsilon, there is only one n1, only one natural number, which I am going to call it as n1, which works for all z inside your compact set, that is mod z minus z naught less than or equal to rho. So here the n1 chosen is not dependent on any particular z in your disk. It is true for all z, because I know that fn of z is uniformly convergent to f of z. Then you have started to do some modification, and at last you have shown that mod fn dash of z minus f dash of z is less than epsilon for all n greater than or equal to n1, and for all z which is in that disk, that is mod z minus z naught less than rho. That means here your n1 was not dependent on any z inside your rho. Hence we say that fn dash converges to f dash of z uniformly in that compact disk. Fine. You can just go through the theorem. It's quite easy from here. But if you are going to including the part which I said to delete, then you may get confused. Fine. So you can skip that part and you can start from page 3 of your notes. Fine. You can just delete that thus fn dash of z converges to f dash of z in the third page, and you can start from second line. That will be the proof. Fine. If you have any doubt, you can ask me later. So ultimately what we have showed is fn dash of z converges to f dash of z in this closed disk, right? But my task is to show that it is convergent in any compact set, any compact subset of omega. And we know that any compact subset of omega may not look like a disk. It might be having any shape. So how to show that fn dash of z is converges uniformly to f dash of z on any compact set, not just on this disk? That is what has been written in the next line. That is, if k is a compact subset of omega, then it can be covered by finite number of closed disks as above. Then it can be shown that fn dash of z converges uniformly to f dash of z on k. I am going to skip this part. I am leaving this as a task for you to find how is this true. If k is any compact set, still how can I prove that sequence fn dash of z converges uniformly to f dash of z on k? You can just try to give a you write a proof and send me. If it is right, I can say you. Fine. So once if you have proved that fn dash of z converges to f dash of z uniformly on k, then you can, on any compact set, then you can easily show that any higher derivative also same thing holds good. Fine. Okay, this is the theorem, and there is some picture which might help for this purpose, not the one which I said to skip. Fine. Other than everything is fine. So we'll go to the next theorem, which says that it's a Weierstrass theorem for series of functions. So keeping exams in point of view, the question may appear that prove or state and prove Weierstrass theorem for series of functions. So you can't just write what is given here. What you have to do is you had to prove as you have proved it for Weierstrass theorem for sequences. Fine. So what is, so we need a sequence, right? We have Weierstrass theorem for series of functions. These kind of questions you have already done many times. Because I know that any series I can write it as a sequence of partial sums. So that is what is given in the proof. So you have partial sums Sn of z, which is summation fk of z, where k runs from 1 to n. So proving that the whole series, the infinite series, converges uniformly is same as showing that this sequence of partial sums Sn of z converges to f of z uniformly. Fine. I think again not much detailed explanation is needed here, because Sn of z is nothing but a finite sum of analytic functions. So Sn of z should also be an analytic function. So you have a sequence of analytic functions converging to the function f of z. So again f of z should be uniformly convergent. Fine. Again you can show that sequence fn dash of z converges to, series fn dash of z summation n from n from 1 to infinity will converge to f dash of z on every compact subset of omega. Again I have sent you some notes on this. Fine.